Hi class, and welcome back to 6802. I wanted to start by just reminding us of where we were 2 weeks ago before spring break. So the major result we had proved was the Whitehead theorem. What that said was that if we have a map between CW complexes, which induces isomorphisms on pi n for all n, then it's a homotopy equivalence. And in the particular case where the map was the inclusion of a subcomplex, we got this stronger result, which was that X was in fact a deformation retract of Y. So the subcomplex, so the total complex deformation retracted onto the subcomplex. I don't remember if I talked about this, so covering all our bases. Any map which satisfies these hypotheses, so induces isomorphisms on pi n for all n. So these F lower star maps are isomorphisms on pi star, is called a weak equivalence. Sometimes people call these just pi star isomorphisms. But weak equivalence is standard, so you should know that definition. Using that definition, we can restate the Whitehead theorem as saying that for CW complexes, weak equivalences imply homotopy equivalence. So if a map is a weak equivalence, you know by default that it's a homotopy equivalence. It is known, it's easy to prove, that the converse is true. And that's just always true. So homotopy equivalences have to induce pi star isomorphisms because of functoriality of pi n for all n. So let's just remind ourselves of a couple of the steps that went into this so that we're really kind of like jogging in the same place. So our proof relied on induction and induction on cells and using the mapping cylinder of the map F, and then using the compression lemma. So in case people forgot, mapping cylinder is that thing that looks like it looks like a cylinder with X on one end and Y on the other, and you're gluing along F along the one end of that cylinder. So recall this compression lemma, which I think reappears in the homework, so it's important to know. So if you have a CW pair, X and A, and Y and B is another pair where B is non-empty, then having the hypotheses that for all n such that there are n cells in X minus A, pi n of YB, Y naught is trivial for all base points. Then you get to conclude that every map is homotopic relative A to a map landing inside of B. So if you have a map in all of Y, you can compress it down to one inside of B without changing what it's doing on A. So we used this compression lemma and a kind of complicated inductive argument to make sense of the Whitehead theorem. And I emphasize that if you understand the proof for when the map F is cellular, you can that's essentially the proof that matters, and the compression lemma is just used once there, but then we also found a way to use it even when F is not cellular by analyzing this mapping cylinder kind of in general. But moving forward with the rest of this lecture, for this week, we're going to be talking about cellular approximation, which is one of the tools that we could have used to get Whitehead's theorem, but we weren't using it. So an important consequence of Whitehead's theorem is this corollary I have stated here, which is that if X is CW and has trivial homotopy groups, including all higher homotopy groups, then X is in fact contractible because X has to deformation retract onto its base point. So, and recall, saying pi star is trivial means that for pi 0 in particular, we have only one connected component. So this is just a simple consequence of the Whitehead theorem. Hatcher kind of ends out this section by discussing the extension lemma, which is maybe like a spiritual sibling of the compression lemma, which says that if XA is a CW pair and you have a path-connected target space Y, if for all n such that XA has an n cell, you have that Y has pi n minus 1 trivial, then F from A to Y can be extended to F bar going from X to Y such that if you include A in to X, so let's make a little hook arrow, this diagram commutes. That's what it means for it to extend. And what is the proof for this? You just induct over the skeleton for X. So let's assume that we can extend for X to the n minus 1. And then we want to make sure we can do it for all of the n cells. So if the n cells are, if En is in A, we're done. We just extend by using F, right? But if En is in X minus A, we have to make sure we can do some work and use our hypothesis. So if En is in X minus A, En is attached by a map going from Sn minus 1 to X. And then that has to live in the n minus 1 skeleton of X. Attaching maps have to land inside of that. So we already know that we have this extension F bar to Y. And this composite is an element of pi n minus 1 of Y. And by assumption, this is trivial. This is 0. Assumption. Let's scroll up. So then we also know that this map is null homotopic. So Sn minus 1 to Y is null homotopic. Which we know it is because it's an element of the 0 group. If and only if it can be extended over the disk. So we actually know include Sn into Dn, and so this is in fact, here's our En cell that we're trying to attach in X. We know we can extend over Dn because, in fact, the data of that extension is just the null homotopy. And that's it. Now we have the map from of F bar on En. So F bar on En is just this map right here. So let's QED that. So moving forward, let's talk about cellular approximation and cellular maps. Okay, so let's start by discussing what a cellular map is, reminding ourselves. So let's assume X and Y are CW complexes. Then a map, so let's say definition, map F, X to Y, is called cellular if and only if it takes X is N skeleton and maps into Y's N skeleton. So it has to take N cells to N or less than or equal to N. How should we do this? Map to K cells with K less than or equal to N. Yeah. Now, cells don't actually have to go specifically to cells, but they land inside of the N skeleton. So what I said here is the most precise definition. Yeah. So in general, cellular maps preserve or reduce dimension. Yeah. So what cellular approximation says is that, let's give this a name, cellular approximation, is that any map between X and Y, where X and Y are both CW, is homotopic to a cellular map. Furthermore, if F restricted to A, where A is inside of X, is some subcomplex, is already cellular, F can be extended to this cellular version, let's say F cell, relative A. So you can do it without changing what the values are on A. So let's prove cellular approximation. So proof. Okay, so what we'll do is we'll induct on cells, because that's always what we do for cellular anything. So what we'll do is assume F on Xn is cellular. Let's make this at Xn minus 1. So on the N minus 1 skeleton, you're already cellular, and you want to extend that to the N skeleton. So want F from Xn to Y, cellular. So in a sense, this is, and we want to do this in a way that doesn't change the N minus 1 skeleton so that we can believe this, we want this homotopic version of F. Yeah, so how do we do this? What we do is we let En be an N cell of X. Then the boundary of En minus 1 is attached into the N minus 1 skeleton, so where things are already cellular. So boundary, En minus 1. This looks like Sn minus 1. This is already being attached by some characteristic map into X n minus 1, where we have this map F landing in Y, which is cellular. So this factors through yn minus 1 living inside of Y. Okay, because that's what it means to be cellular. So we already know that the boundary of the cell lands in the n minus 1 skeleton of Y. So F of En, which I mean on the interior of the disk, or on the disk. Where does it take the whole disk? This is a compact set in Y. Since it's a compact set, it intersects only finitely many cells. So because Y is a CW complex, and we are picking some compact subset, you can't have a compact subset intersect infinitely many cells, because then it wouldn't be, I want to say closed and bounded, but it fails to be compact because it's open, it's covered by, each of those cells plus a little open neighborhood, and that's you can't pick a finite subcover of that. So so we have this issue. So what we'll do is make a list of those cells. So let we'll call these FEY. I don't know. We'll call these EK. Be the collection of cells, or it's a finite set of cells in Y with non-empty intersection of this image of FEN. Are intersecting for all the guys where K is less than or equal to N, we don't care. So for EK with K less than or equal to N, do nothing. So you extend F to those, like if this collection is only cells of degree less than or equal to N, then F is cellular. And so our goal will be to deform F so that if there are any cells EK where K is bigger than N, we can miss them. So let's write that. So if EK exists with K strictly bigger than N, we want to deform F to miss EK on EN. And I kind of apologize that these are all using the same notation. So just to be clear, En is on X, En minus 1. That's just a mistake. Let me correct that. Sorry. This guy should be up here. This should be En. En's boundary. Yeah, that looks good. So these guys are on X. These guys are on Y. Here's a Y cell. X cell, Y cell, X cell. That looks good. Okay, so if we want to do that, all we have to do is make sure the image misses a point. In EK. So here's my like loose picture is whatever this cell looks like. Here's EK in Y. We have this, image of EN from X. This guy's in Y, right? And we want to know that this thing at least is missing some point. So, right, so like this point over here, F is missing on this cell. So what we can do is just retract this all the way to the boundary by just picking some, punctured, some retract of the punctured disk onto its boundary. The punctured, here it would be K disk onto its boundary. And in doing, following that homotopy, what that will do is take these, take F and retract it somewhere onto this boundary as well. So then the new version of F will kind of walk along and not go inside of EK. It will only intersect the K-1 skeleton. And so now we've reduced the dimension of the cell that it runs into. And so then what we do is we will induct, or will just for loop over E, K in descending order. For K bigger than N. So we'll start with the biggest dimensional Ks. We'll do all of those. We'll homotopy them all at once. And then we'll do the next dimension down, then the next one, and we'll reduce that down to N plus 1. And then eventually everything will now be hitting only the N skeleton. So here's the annoying part of this proof, is that that's basically a side lemma. So we're going to assume that this map from dn, so here's my copy of en in X, mapping under F to Y, and we're taking some restriction of this, we're taking the subspace of this that actually hits EK, misses can be homotoped to miss a point. In EK or Y, provided K is strictly bigger than N. So this is some sort of dimensionality argument, but we're ultimately only checking it on maps from some compact subset of this disk, dn, mapping into this one particular cell, EK. And so this is sort of boiling down to one map up dimension from a dn to a dk, k bigger than n. And so your picture for this should be you've got this closed disk, and over here we've got the solid ball. And it doesn't matter how you're going to map this in, we can homotope that map so that it misses a point. Yeah. So we'll come back and prove this after. But let's first just close out the proof. So induct, it's really not an induct, but we're doing an induction on a finite set. So induct down on K. So pick a random k cell where k is maximal in this set. So ek in y has a non-zero intersection with f of e n x. So what we do is we assume we have a homotopy f, which we can homotope f from as a map of x n minus 1 union e n. So union this one cell, we have a homotopy, so this is a map to y. We have a homotopy to f, let's just call this f bar. Why not? Same source and target, right? And this is a homotopy rel x n minus 1. And we'll fit that into this assumption up above, which will be annoying and technical, to miss a point. So such that f bar, how do I want to say this? Such that there exists a y in e n e k y in the interior of e k y. Where f bar of e n x does not contain y. So, under that assumption, we can further homotope e. How should we do this? We should homotope y minus y naught. Let's go. This is the k skeleton of y minus y. Deformation retracts onto yk minus ek. So we're just taking out this one cell. So this looks something like we've got, y is continuing on, it's got more stuff, right? But we're missing this one cell, and we're now doing this retraction coming from the retraction of the punctured disk onto its boundary. And this gives us a homotopy which we compose with f. So we've got this picture. We've got x n minus 1 union e n x lands in y minus. It lands in yk because we're inducting down on k, so we're landing on yk minus y. And we know that this is deformation retracting onto yk minus the interior, or minus, interior, ek interior y. Cool. And this new map will be, we'll call f twiddle. And so then remove ek from set, because no longer is f twiddle intersecting with it. So use f twiddle instead of f, and recursively iterate the proof until you're down to the base case we talked about. Then what you've done is you've produced a homotopy between f and a new f twiddle cell. I don't know, which I guess I'm calling twiddle because it's one of these f twiddles, and it's f twiddle cell because it's finally cellular. So which is cellular on xn, and this homotopy happens relative xn minus 1, as desired. So, what makes sense, right? So, provided we first start our base case at degree 0 and homotope this map to take a base point to a base point, like, we're good, right? That's just, we're requiring the target space to be path connected, so that's fine. And then we induct up the cells, and we can now make it cellular at any skeleton, which means it is in fact cellular. And on the next page, we'll discuss what's going on with this technical lemma. I should say, if you want to get, if x has infinite dimension, as usual, we can use this trick where we take the homotopy for degree n, on the interval like 1 over 2 to the n to 1 over 2 to the n plus 1 n, something like that, right? And shrink the homotopy happening in the whole complex to one happening in, finite unit time. And we've used this trick before, so. And also the assumption that we can do this relative some subspace where it's cellular should be straightforward, because clearly this induction is never going to touch or do anything to the cells on which the map is already cellular, right? It's not doing anything to the n-1 skeleton, and it's also, if this set of EKs is empty, there's just no effect of the homotopy. So that explains the entire statement of the theorem. So let's unpack this technical lemma that we need. I should note before really saying this that I think up until I decided to teach this, I just believed that it's true that you can homotope maps of disks into higher dimensional disks to miss a point relative to their boundary, in the way that is required above. But why can we do that? So here is the formalism that will let us do this. So, and the way that I really want to line up this lemma to look like what we care about before. So we're looking at a map F from IN, which is our replacement for DN, but we're going to want it to be, identified with this rigid linear subspace, right? We want things cubical. And Z is going to be our K skeleton. So the map that we're looking at here is the map from DN, which is EN, which includes into X, N, and then maps via F to Y, K, where K is bigger than N. Right, so we have this map, and Z is supposed to be subspace W adjoin a K cell. So what I want to think about is that Z is equal to YK minus EK union EK. So our W is going to be that guy, YK minus EK, for the purpose of this. And we have this K cell. So then what we can do when we have a map from a disk into a space which is formed by adjoining a single K cell to some subspace, we can homotope that map. So we're starting at F, which is F0, and we're going to homotope to this map F1, which has nice properties outlined below. And it's a homotopy of IN relative the preimage of whatever, or IN, paired with the preimage of EK, so of that K cell, mapping to Z relative that K cell, so that's YK, right? And the thing we're not going to change is F inverse of YK minus EK. So what that means is that we get to homotope our map. So in our case, we have this map DN, which looks like EN in XN mapping to YK. And we're going to homotope it to this other map. So here's F0. This homotopy to this other map, DN F1. And this is going to happen relative the preimage of YK minus EK. So in particular, that's relative XN minus 1. And in fact, which includes the boundary of EK has to map into something like that, right? So I guess I should maybe be a little careful. It's not quite that, except in the base case of the induction. It's something like relative where the boundary is sent. So relative xn minus 1 and the boundary of en. Boundary of en. I guess, which is also an xn minus 1. I guess that's what I mean. Yeah, that's good. Okay, so the technical details here is that what we're going to require is that there's a polyhedron inside of IN. So what that means is some closed convex space which is made up of, it's exactly what you imagine a polyhedron is, right? Like inequalities determining linear simplicial type space. So we've got this region like this, looks like K, inside of IN, such that F1, our new map, takes K into EK. So over here in Y, I guess I'm going to scroll. Let's get myself some space. Still want everything visible. It's okay. Right, so it's mapping this over here to Y, and we've got this, whatever, here's EK, right? So K lands inside of EK. So here's F of K, right? F1 of K, kind of bad. And F1, when restricted to K, is actually piecewise linear. Now, piecewise linear means that I'm taking EK, which is blobby, right? It's something in some abstract topological space, and I'm turning it into a subspace. I'm identifying it with RK. And so now when K is mapped over, K, lands in some sort of, here's F of K, some sort of image. What I want is, I'm not going to require that the map be linear on all of K, so just be a linear transformation from K over here is living inside of Rn, right, to Rk, but I will require that it, after subdividing K into little polyhedral subdivisions, on each one, it is now linear, and I still want it to be continuous, so it's like a continuous, it's a piecewise function that's defined on little subdivisions, which is required to be linear on each one. Okay, and then the other important feature is that there's some bit of EK which is missed. So now to make sense of the second one, I need to boost dimension a little bit. So let's go down a little. So here we're really assuming that we're mapping from some low dimensional thing. So let's say this is my Rn, and here's my little K, right? And this is now mapping up into over here in, so this is an En, and here we're in Ek, and I identify it with, let's say, R2, right? Let's say K is 2, so I'm going to require K is bigger than N for this to make sense. Now, K is piecewise linear, so its image looks something like one of these sorts of things, a bunch of intersection of hyperplanes. So there's some open U whose pre-image under F is entirely contained in K. So you have an open set, let's say maybe something like this, U, and its pre-image only lands in K. So this section here of K, where we F1 inverse of U, looks good, right? Now, the problem is that U is now a two-dimensional open set in, it's a open two-ball up to homeomorphism type in, or disjoint union of them, in R K. And because the image of K is this compact set, and contains these finitely many little hyperplane segments, you can only intersect that in a finite number, in a finite number of hyperplanes, and in particular, those can't fill the space in U. So there has to be a point that we miss here. So there has to be some point, let's just call this P. So then exists P in U such that F of F1 of K does not contain P. So just by eventually dimensional arguments about maps from Rn low dimensions to Rk high dimensions, you discover piecewise linear maps, which we completely understand. You can see that there's no way to write a piecewise linear map on a tiny little compact set that will fill all of U. So it will always miss at least one point of U. And that's how we end up using the result, right? now how do we actually prove this result? Okay, so this proof is honestly just kind of insane. Let's piece through this. So, what we're going to do is we just fix first our identifications. So we're really just looking at a map. Just consider the map from IN over to this cube, which is our replacement for EN, to RK, and we are definitely requiring K to be bigger than N. For actually, I guess we only care about K bigger than N, but I think this is still true even for. Don't think we need the dimensional bound, but we do need it to get the missing a point part of U. Otherwise, U can be covered, and it's just not interesting. Okay, so RK is our replacement for EK, the interior of it, right? Okay, what we're going to do is over here in RK, we take two open balls, or two closed balls. Here's B1, and here's B2. And we can honestly just take these to be the unit, the radius 1 and the radius 2 balls, closed balls, at the origin. In RK. Okay, and we're going to look at their pre-images underneath this map. So we've got this. Here's F. Here's F. Their pre-images look, I don't know, something. Let's make it look a little bit. Boop. And yeah, there's a limit to how much wiggling I want to draw. So something like this and something like this. So here's F inverse of B1 and F inverse of B2. I'm drawing the boundaries, but they are closed, right? So notice that we're in Euclidean space, so these guys are compact subspaces of IN, so they're compact spaces. And since these are compact, F is uniformly continuous on either one, but in particular on the bigger one, so on F inverse of B2. Because it's uniformly continuous, we can, because of compactness, right, we can cover this by an epsilon net, like sufficiently small, so that if points are less than epsilon apart in the left-hand side of the board, then they end up being within, radius, within a half on the right-hand side of the board. So this will allow us to distinguish between these two curves, essentially. So what we're actually going to do is subdivide I into cubes whose total radius, whose maximum dimension less than epsilon, which will imply that points in them are closer than distance a half apart after applying F. So we subdivide this whole space. So I'm going to do that. Okay, so what we're doing is putting pixels on the picture on the left. We're just trying to subdivide this into cubes from these messy balls that we have. And we want the pixels to be fine enough to distinguish between B1 and B2's pre-images. So what we'll do is let K1 be the pixelized version of F inverse B1. So what that means is every square here, like this guy, etc., right, that intersects F inverse B1, we're going to union together. So I think it looks like these guys should all be included. This one, I think here I get to like go back. It looks like I got to do that. So this whole region is now going to be K1. You know what? Let's shade it. Yeah. So that guy here is K1. Notice K1 is a compact set because it's a union of balls. Yay. Now, K2 is going to be K1 plus all of the cubes that touch its boundary. So I'm just going to make K1 a little bit bigger. But we've picked epsilon. Like this bound of a half means that even when you add on one more cube, you're still not going to be able to run into B2 because you'd need 3 cubes or whatever to get from B1 to B2. So I think I subdivided far enough that that should be the case. So if I keep going over here to the left, I think I want to include these ones. We'll include even corners. Yeah. So this bigger guy is now K2, and K2 covers all of this. So K2 goes out to here. So we can pick epsilon tiny enough so that we get this like subdivision. So what we have is the following like series of inclusions. We've got like F. Ooh, that's not writing. Yeah, F inverse of B2, and inside of it, but not equal, is K2, which contains not equal K1, which contains and also is not equal to F inverse of B1. So now when we map to the right, we don't have an assumption of piecewise linearity on F, right? So what we're going to get is that K1 will do some sort of wiggly thing like this. So this is what F of K1 is going to look like. And then K2, F of K2 will look something like this. And we again have this sort of nested expansion going out to the right. I've maybe distorted these a lot, but I mean, F could do that, so we have to deal with it. So how are we going to proceed? First, what we're going to do is further subdivide all of K2. So it's made up of a bunch of cubes. Subdivide those into simplices, or just suffer more to write what's happening on cubes. But then, on each simplex, we're going to define a new map. So define a new map on K2. So let's call that G, going from K2 to over to EK, right? Which is, right, this is our RK. And what it's going to be is G needs to be piecewise linear. So it's going to be PL because it's linear on each simplex in the subdivision. Okay, well, we could just make it 0, so what do we want it to be? And we want it to agree on all the agrees with f on all the vertices. Okay, so that's kind of a pain, but the idea is that on each of these little simplices, right, inside of K2, right, f is doing something where it might be distorting this simplex. Right, over here as it maps into EK. But what G is going to do is take the image of each of the vertices, right, and then linearly extend by linear sums to what it has to do in between. And so G is going to be like our wobbled out, remove the wobble version of f just by determining what it's doing on the vertices. Now, what I want to do, if you look back at the previous image, is define basically a bump function. I want to only, I want to do a straight line homotopy between f and g. So, so the only reason to move to piecewise linear land, to move to RK and Rn, is so that I can write down a straight line homotopy. Ultimately, they are the only homotopies we can write down. So I want the homotopy to look something like 1 minus t, I'm leaving space, f, plus t, g. That would be great, right? And so at time 1, it's doing f, I guess. No, it's doing g, and at time 0, it's doing f, right? And this would be our homotopy h, right, of t. I guess I wrote it as f sub t in the opening, but what I like to do is do this so that I am doing the homotopy on K2, but not doing it on the interior of K1. Okay, so think of this little buffer of cubes between K2 and K1 as our buffer between what's going on out at f inverse of D2. And then I've got cubes. Here's my cubes in K2, and then I've got these like inner cubes in K1, right? The K2 and K1 ones, they're our buffer. And then in here, I'm doing, I'm on f inverse of D1, right? And the goal is to bump function so that we're only actually doing the homotopy inside, right, like inside of this local radius. So I want to do, so I want the homotopy to happen only here. So the homotopy changes this, and it keeps the outside part constant. So you should think of this as, like, in our original setup, in case this formalism is just confusing, I'm trying to only alter the function, like the interior, I'm only trying to homotope part of the map on the interior of the cell, as it does something on the interior of the target cell. So I've like looked at the pre-images and I'm separated out those zones, and I'm only moving stuff so that we can eventually dodge one point just on the interior without changing what's happening on the boundary of the cell. Okay, so what we need though is a bump function, but we can now define that. So let phi be defined on K2, and it's going to map to 0, 1. And I want phi to be 1 on F inverse D1. So it should be 1 on K1. So everything inside of K1. And it should be 0 on K2 minus K1. Except that doesn't quite work because I would just be jumping. So what we'll do is it's 1 on the vertices of K1, and it's 0 on the vertices of K2 minus K1, and then extend linearly to all of K2. So kind of what my image is you've got this buffer here where, here, let's just zoom in a little bit. Here's K1, and my F inverse of D1 is in here. And so on all of these vertices, the function is up at 1. Right? And then as I move out, and let's go to blue for my next line of defenses or whatever, right? So now on the vertices of K2 minus K1, that's going to be things like this guy, this guy, this guy, this guy, and this guy, and this guy. So 0, 0, 0, 0, 0. And I'm really assuming I've subdivided these simplicity, so let's just say they've got a lot of extra faces and stuff. So in between, it's going to be linearly decreasing in between these guys via linear extension from the vertices. So you end up with a function which is, I don't know if we did a side profile, like if this is K1 and here's F inverse of D1, and then this is K2, K2's boundaries, then our bump function is going to be 0, and then linearly increases up to being 1, then linearly increases down as you go out on K2. And so what do we do with this bump function? We just add it into our homotopy like that. So now it's not being F, but the part that T is changing, T is only doing something if you are where this bump function is 1, and it's linearly interpolating between it as you transition on K2. Yeah, and so we have something that's not doing anything out at F inverse D2, and it is doing something in at F inverse of D1. So it's not doing anything at F inverse D2's boundary, and it is doing something on the interior. Okay. So as stated above, I only defined Ft on K2, but we extend Ft to all of in by the constant homotopy on in minus k2. So we now have this buffer region, and at the boundary of k2, it's not, nothing's, the homotopy is constant. And so that means that we are in business. So our claim moving forward is that this homotopy, let's define F1. Oh, F1 is the target, the homotopy. So this now takes in minus k1 to you know what, that will be open. Let's take the closure of that to a compact set. And it's a compact set in the target, which misses B1. Missing 0 in particular. Okay, so how do we prove that? So the first thing is that on in minus k1, ft is constant. On in minus, I guess in minus k2. On in minus k2. Okay, my subscripts and superscripts are dying. I upper n minus lower k lower 2. Okay, well, what we know is that by construction, we had this ordering of sets, right? So we had f inverse of B2 containing but not equaling K2, containing but not equaling K1, containing but not equaling f inverse of B1. So what we do know is that in minus K2 does not intersect B1. Yeah, so yeah, let's write this as this. F1 or FT takes better way to write it. FT of in minus k2 is disjoint from B1. So intersect B1 is the empty set, because K2 strictly contains f inverse of B1. So nothing else, nothing which is hit by B1 could land in F. Yeah, could be outside of K2. So, and then if we're in between like K2 and K1, if we're in our little buffer zone, so if sigma is a simplex of K2 but not K1, we know by granularity of epsilon that F sigma fits inside of a ball of radius 2. Has diameter, radius 1/2. So this fits inside of, let's say, B, where B is a ball of radius 1/2, right? And so remember, we're at the origin, we've got this ball of radius 1, we've got this bigger ball of radius 2, right? And we have some other simplex. It fits inside a ball of radius 1/2. So because sigma is not in K1, sigma has to at least contain, or F sigma has to at least contain some part outside of that ball of radius 1. So part of it could run into there, but it has to expand out. And then if you look, that point there is at, most distance 1, so the closest this point here could be is 1/2 from the origin. So in particular, F sigma intersect the ball of radius 1/4 at the origin is empty. And so this now means that F1 takes anything in IN minus K1, its closure, to something that misses 0, and in particular is missing this whole open set. So F1's image lands in the complement of this open ball, which means it's compact. Also, it's bounded, because IN is compact. Yeah, we're good. Okay. So, yeah, this is our conclusion. So this gives us the desired conclusions. The construction of the homotopy implies that F1 is PL on the interior of B1. I guess I mean it's PL on all of K1, because we've done that homotopy. And F1 misses 0 and an open neighborhood. Of it. So you can take that open neighborhood to be U in the definition, but for our conclusion, we actually care more about this fact that we're missing this point. And that completes the proof of cellular approximation. So let's give a few more consequences. Okay, so our first consequence is we can also do this for pairs. So corollary 1, cellular approximation works for pairs. Works for maps of pairs. So if I have f from x, comma a to y, comma b, and this is not an inclusion necessarily, what we can do is take f as a map from, just restricted to a, mapping from a to b, replace it by a cellular map, and then we can extend that to a homotopy, since MXY is a good pair. XA is a good pair. So we can extend that to a homotopy. This homotopy between F and F twiddle cellular. So we can extend that to a homotopy, and the homotopy will now, let's just call it FT, I give up, will now go from X comma A to Y comma B. So I'm extending it to a homotopy on which agrees with F on X at time 0, and agrees with the homotopy which is provided on A to B. So, but then it doesn't necessarily give you a cellular map on all of X. So notice that F1 restricted to A is cellular, but F1 restricted to X, not necessarily. Great, but now F1 restricted to X is cellular inside of A, and we said that, in fact, our proof gave a homotopy of this map to one that's cellular on all of X without changing what's happening on A. So now we can do another homotopy. F1 gets homotoped to, let's just call it F2, where F2 is, I should say, rel A, where F2 cellular. And then that map by inspection is still mapping A to B, so this is F2 is now a map of pairs X comma A to Y comma B, and it's cellular. And that's our proof. Should have labeled this. Say proof. Let's put a box at the end. Okay, so that's like the first corollary you can get. The next is that for maps of spheres, we have that pi k s n. I think I'm now switching my relationship between k and n that existed throughout the whole thing, but whatever. This is 0 for all k strictly less than n. And so our proof will now be, if you have any map f from sk to sn increasing dimension, we can homotope it to be a cellular map. And so that new map, let's call this F0, F1, is mapping from SK. Well, SK is its own Kate skeleton, and it will map into SN's Kate skeleton, but SN's Kate skeleton is just a point, because SN is just that 0 cell union, an N cell. There's one good cellular model for it, so its K skeleton is contractible. And that means that F1 is null homotopic. So, or rather F is null homotopic. So F is homotopic to F1, which is homotopic to the constant map. And so sometimes people like to refer to this as the idea that any, the heuristic for why there are no low-dimensional homotopy groups of spheres, by which I mean maps from lower-dimensional spheres into higher-dimensional spheres that are interesting, is because they always, quote-unquote, miss a point. And that's true, but it's true because we can homotope them to be cellular, and the cellular ones have to kind of respect dimension. And once you do that, you do away with any concerns you might have had with, like, space-filling curves, or other sort of curiosities. So those maps still exist. They can still be continuous, but the whole point is that they are homotopic to maps that miss points, because they're homotopic to cellular maps, and then the cellular maps are, in fact, null homotopic. So I think that's a good place to end it, and we'll pick up next time with the next step in this idea, which is to approximate spaces by CW spaces. This is known as CW approximation. So, see you then.